Hello, everyone. So last time we talked about how we can predict the chemical potentials of a mixed species through the use of its partial pressure. And if we're really lucky for an ideal species, I can predict the partial pressure of a mixture simply based on the mole fraction uh, of the species I'm interested in and the vapor pressure if it was a pure species. However, it turns out that for a non-ideal system, this can get a little bit messier. And again, as a reminder, a non-ideal mixture is essentially any sort of mixture where the IMFs are going to be different in the mixed state as than from the pure state. So for example, if I'm looking at, say, acetone mixing with carbon disulfide, we run into some issues because it turns out that while we often think of acetone as uh, nonpolar, you'll notice that it does actually have a decent dipole. Whereas carbon disulfide has absolutely no dipole, and so is thus nonpolar. So if you try and put these two together, it doesn't end so well, as essentially the acetone is going to want to tend to hang out by itself, and the carbon disulfide again, likewise. And because of this, it means that the IMFs holding the carbon disulfide in solution are much weaker. And so it's much more likely to evaporate in the mixed state than essentially in the pure state. Well, we can use Raoult's law to go ahead and describe the solvent region, where essentially the carbon disulfide is more or less the entire solution, and likewise for acetone. However, we often have to worry about what to do in the middle. And again, this becomes really uh, troublesome because of the nature of the differences in IMFs will cause a great deal of variety in how these systems interact. So for example, if we have a system like carbon disulfide and acetone, where the IMFs are essentially net repulsive, essentially we lack the same attractive capacity as in the pure states, then we're going to generate this negative deviation. The system's more likely to evaporate. Uh, and if I have a system where the IMFs are more favorable for the mixture, we're going to see a negative deviation. And that essentially the vapor pressure is going to be lower than would be expected from a Raoult's law, essentially saying that the system doesn't want to doesn't want to evaporate, which we'll look at a case like that in a little bit. But essentially, what ends up happening is that honestly, in this middle region, it can be very hard to describe a non-ideal solution. However, there is another region where you may notice that our solutions actually behave fairly nicely. And that's essentially at very small mole fractions, you may notice an area that can almost be considered linear. Now, this area may actually be fairly short and that it will quickly break down, but oftentimes, such as in carbon disulfide, you may get, say, a mole fraction of about zero point 0.1 or 0.5 or 0.05 before it breaks down. And it's worth noting that that still can be considered as somewhere up to about 2 or 3 molal, depending on the molecular weight of the species involved. So oftentimes, this is sufficient enough for a lot of our solutions that we're going to examine on a daily basis. And so by trying to essentially treat this linear region, we're going to essentially assume that we're going to be looking for essentially what's called a dilute, a ideal dilute system, where essentially I'm looking at the solute behavior, where essentially I'm looking at the mole fraction of B when it's the minority component, and I'm going to essentially fit a straight line. And then what I can do is, instead of modeling the vapor pressure of my solute on the mole fraction and the ideal vapor pressure, instead I say, well, that straight line's not going to work for me here. Instead, I'm going to fit this straight line that essentially will intercept the pure phase at, say, some arbitrary value k. And this is essentially our Henry's constant, because this whole setup is called Henry's law. And again, one of the important things is that k isn't actually a real real pressure that you can obtain. Instead, it's really just an experimentally determined parameter that says that if I obeyed Henry's law to the solution limit, that would be the pressure that I would get. And it's worth noting that the Henry's constant and the uh, and the pure vapor pressure can often vary quite significantly. And again, if I have a positive deviation from Raoult's law, I'd expect my Henry's constant to be greater, and if I have a negative deviation, I'd expect it to be lower. And again, if a system obeys Henry's law, it's called an ideal dilute solution. So a way to think about this is that it behaves under ideal conditions, or it has this ideal linear behavior, but only under dilute conditions. Thus, the name should hopefully make a great deal of sense. And again, one of the important things to make note of when you're using Henry's law is that in general, it will actually break down fairly quickly. And it's fairly rare to find a system that holds up to a mole fraction past about 0.2. And oftentimes you're not going to want to trust it much past 0.5 or 0.1. But what ends up happening is that when I stitch Henry's and Raoult's law together, I actually get a pretty good description for mixtures. For example, if I'm caring about a solvent, I'm going to make use of Raoult's law. But if I'm caring about a solute, I'm going to make use of Henry's law. Thus, it's very important to make note of what set of conditions each component of your mixture is under in order to know how to treat it properly. And so in general, Raoult's law is going to be very good for treating our solvents. Say, in this case, when I'm looking at chloroform mixed with acetone, it turns out that if I have a mixture of that's mostly chloroform, I actually have a pretty good chloroform tends to obey Raoult's law fairly well. We have a nice linear region. Similarly, under this case, acetone is obeying Henry's law fairly well. But one of the things I want to make note here is that you may notice that acetone in this case shows a negative deviation from Raoult's law. And as promised, this is an example of how a negative deviation from ideality can happen. Because if I mix acetone with chloroform, well, it turns out that chloroform with a slightly electropositive hydrogen doesn't actually do that great of a job hydrogen bonding to itself. It's one of the reasons it's so volatile. However, as soon as you mix it with acetone, well, acetone has this nice negatively charged oxygen that doesn't do such a great job forming a polar bond to itself. So when you put these two together, it turns out that they're really happy together because oxygen and the hydrogen finally get the partners that they want. So the mixture is way more happy than the individual components. And again, that's exactly what you see under these conditions, is that at all points, essentially, the vapor pressure of these systems, of the mixtures, is much lower than we would expect from a simple Raoult's law treatment. So again, using Henry's and Raoult's law, we can actually describe a lot of practical solutions that you're going to work with, because in most cases, we tend to have a system that is a clear solute and a system that is a clear solvent. So the real trick is going to be trying to figure out ways to describe the regions in the middle. And one way we can do this is by taking a little bit closer look at the thermodynamics of mixing, which we'll go ahead and do next time. Till then, take care.